meeting today. Recording in progress. So this is an announcement about recording of this talk. If you don't want to be recorded, just switch off maybe not everything, but you can mute or you can hide camera. So our speaker today is Maciej Kolanowski, and he will talk about asymptotically de Sitter spacetimes. Please begin.
Thank you. I want to tell you about some recent work we've done with Professor Lewandowski. Part of this talk was also in collaboration with Professor Ashtekar. I'm afraid that we are starting some very bad tradition here at this seminar, because this is just like the last talk and the talk before by Professor Tafel. It is based upon yet unpublished work. So I hope that we will manage to announce it more clearly to the world next month. So I will talk how to define conserved charges, or rather unconserved charges, in asymptotically de Sitter spacetimes. Why should we actually care about asymptotic? Oh, okay, now it works. Why should we care about asymptotically de Sitter spacetimes? First of all, because according to all our observations of the universe, we can see that the universe is not only expanding, but the rate of its expansion is growing. So we have something like a cosmological constant. It's not necessarily it's not necessarily a constant. It could be some dynamical mechanism generated by some vacuum expectation value of some sort of a dark energy of something, let's say. What I'm about to tell you mainly doesn't really depend on cosmological constant being a constant, so it can be somehow dynamically generated, assuming that fluctuations about this vacuum have some proper asymptotics, that they don't get too large during late stages in the universe history. So what's the problem? I mean, charges for, say, gravitational radiation were defined a few decades ago, and in the meantime they were defined in all possible ways using very different approaches. There is also a lot work on asymptotically anti-de Sitter spacetimes, and there are hundreds of papers literally about it. So why can't we just copy paste results from those? So there are a few differences. Now I'm just going to signalize them and talk about them in more details later on. So first of all, scry, null infinity, is space-like hypersurface in asymptotically de Sitter spacetimes. So as a result, we don't have any killing vector defined on this any time-like symmetry on this hypersurface, which we could use to define some notion of energy. Whatever charge we can define is going to be non-positive in general. I mean, not necessarily positive. Okay, let's say it. It can be negative. It can be positive. We don't exactly have control about it. Moreover, as we will see, there is no universal structure on this scry. Or to put it a little bit differently, there is a universal structure, but this is only a structure of a smooth manifold. So asymptotic symmetries that preserve universal structures are simply diffeomorphisms of this, and that's a lot. We have no, a priori, we don't have any distinguished generators which we could use to define charges. So we have too many charges, basically, if we even can define them.
Excuse me, may I have a comment?
Of course.
So the problem with Scry is that we are looking for generators for asymptotic symmetries. And there is possibility that there are privileged sections of the Scry instead of the group. So somehow nonlinear counterpart of the group. And this is the remedy for all these problems. And unfortunately, I cannot stay till end of this lecture because I'm teaching soon, but I want to make this remark.
Thank you. Yes, this is true. And in fact, I will tell something about it. We have some idea how to define those privileged sections. It may be that they lead to some distinguished group, but well, not necessarily. So thank you. That's very on point, and I will address it later on. And there is obvious question that I will comment on at some point. Can we actually measure differences? So is it going to be, is today's talk about some mathematical exercise, or is it, or can it be connected to observations, not necessarily today, but say in 15, 20 years? We'll see. So I will start by some hopefully pedagogical, some hopefully clear introduction to the topic of asymptotically de Sitter spacetimes. Then I will talk about the idea of Wald and Zoupas, how to define non-conserved charges. They did it for asymptotically flat spacetimes. We're going to do that for asymptotically de Sitter spacetimes. Then in point 3, I want to tell you a little bit about this idea, how we could perhaps distinguish some symmetry group in all those diffeomorphisms, exactly by choosing some preferred foliation, as Professor Jezierski suggested. Then we, time permitting, we'll discuss some examples, and well, that will be it. So I will start by some mathematical definition. So we start with a physical spacetime, and we kind of extend it to a little bit larger spacetime by attaching a hypersurface. It's going to be Scry, and conformal transformation of metric. And we have some technical conditions that on this conformal factor. Basically, we want it to be non-degenerate on this Scry, so that we can, I mean, we want it to be 0 on Scry, but its derivative non-vanishing, so we can use this conformal factor as a variable. At Scry, so this is for now the same as definition of asymptotically flat spacetime or asymptotically anti-de Sitter spacetime, and of course the difference I'm sorry, of course, the difference lies in Einstein equations, and obviously in Einstein equations it should be R instead of this 1 over R. And here we assume that this cosmological constant lambda is positive, and we also can have some sort of matter which vanishes fast enough. This is actually slower vanishing that is required in asymptotically flat spacetimes, if I remember correctly. So it is actually satisfied in most of situations one could be interested in. Are you trying to write something? Okay, perhaps not. So what follows from this definition? As I said, it's technical, it's not very important right now. So first of all, it follows actually that Scry is a space-like surface, three-dimensional, of course, in contrast to asymptotically flat spacetimes where it is null, and asymptotically de Sitter spacetimes where it is time-like. Moreover, it follows from Einstein equations that Weyl tensor vanishes on this hypersurface. Notice that it doesn't imply any sort of conformal flatness because it vanishes on hypersurface of codimension 1. You would need it to vanish on some neighborhood, so on a three-dimensional set to imply conformal flatness. The second bullet is actually easier to prove here than in asymptotically flat spacetimes, because in asymptotically flat spacetimes, to prove it, you need, it's a global statement. You need to know something about topology of your scry, but if you have non-vanishing cosmological constant, it's a local statement. It doesn't depend upon a topology. What is not specified in this definition is, well, first of all, topology of scry. Usually I think always in asymptotically flat spacetimes, we assume that scry is a cylinder, that it has a topology of line times a sphere. But it's not specified here, and we will see that it can be, roughly speaking, anything. And also boundary conditions at scry are not specified. So in asymptotically anti-de Sitter spacetimes, where scry is a time-like boundary, you need to specify some boundary conditions. For example, that metric induces conformally flat, and this is needed to have well-defined Cauchy problem. Here we don't have it, and it would be actually unphysical restriction to put any restriction on this boundary data, as we will see. Okay, so let's now go to some examples. This is the Sitter metric written in so-called global coordinates. And you can see immediately that the Sitter is topologically line times three-dimensional sphere, and then we take quite obvious conformal factor, and as a result, this scry is, as comes from this product structure, is three-dimensional sphere, and metric induced on it is metric on a three-dimensional sphere. Of course, we need some dimensional factor here, which serves a role of a radius of the sphere, but it can be altered simply by changing this omega. So it's not a physical importance. Okay. Another case, another example is cosmology. Let us assume that we have cosmology with k equals 0. For some reason, so we have topologically our spacetime now is real line times times R3, and this solution looks like this. This conformal factor A is determined by Friedman equations. So let us assume that we have not only omega but also some matter, which is some reasonable matter. So it can be dust, radiation, something like this. Then you can easily check that the energy momentum tensor vanishes fast enough. So it is actually asymptotically flat space, asymptotically de Sitter spacetimes. We have quite obvious choice of this conformal factor because this is actually conformally flat spacetime. But then our scry is going to be R3 instead of S3. So this R3 is S3 with 1 point removed. And metric induced on it is flat metric on R3. And now you could say, okay, but so let us imagine we don't have any matter, we don't have dust, we don't have radiation, we have only lambda. Then, of course, this is just de Sitter, but written in some stupid coordinates, which don't cover the whole spacetime. So the fact that we got scry without one point, this S3 without 1 point, comes from the fact that we used stupid coordinates and stupid conformal factor, which didn't work everywhere. So if we are smart enough, we can deduce the correct conformal factor to make it actually to three-dimensional sphere. But the point is that if we have any matter at all, whatever it will be, we cannot change it. It's going to be R3, and there is no other choice of a conformal factor which would make it three-dimensional sphere. So as we see, this is topologically different situations, and both of those are kind of physical examples, I think. So the third one would be Kottler black hole, which you can also know as a Schwarzschild de Sitter black hole, but actually it was discovered by Kottler, so the credit is due to him. Here it is written in some sort of a boundary coordinates. We can use 1 over r as a conformal factor, and again check that it is asymptotically de Sitter, and which is parameterized by u, which goes from minus to plus infinity, so it is a real line, and a point on a sphere, but this time two-dimensional sphere. So our scry now is cylinder, as in asymptotically flat spacetimes. It is r times s2, which is s3 with 2 points removed. So I think that perhaps you can see some pattern here. And we have some metric induced it. And you probably already noticed that in all those examples, metric induced on scry is conformally flat. So you could ask, is it a coincidence? Perhaps all physical metrics, whatever it means, physical, are conformally flat when induced on. I mean, they pull back to scry is conformally flat, but the answer to this question is no. It is a purely coincidental fact, which is, yeah. So now for a counterexample, let us consider Taub-NUT.
I would like to understand the role of lambda in equation 6. What is the privileged coordinate u? It can be included in u. You can.
Yes, of course.
So this is just d something, yes?
Square. Yes, sure.
So lambda has no role here.
Yes.
Okay, thanks.
So Kerr de Sitter, Taub-NUT, actually this NUT should be with capital letters because those are free names, I'm sorry. It's some sort of a topologically deformed black hole. It was recently shown that actually those spacetimes, even with Kerr parameter, so even when they have mass, they have this topological deformation, and they're rotating, they are smooth, despite the fact that they can have some horizons which are not smooth. They are asymptotically de Sitter, at least for some parameters. I'm not sure if it is true for all parameters, but at least for some parameters, scry is a three-dimensional sphere, actually. But generically, metric induced on it is not conformally flat. So it is a counterexample. So I have a few questions about it, and during this talk, I will ask a lot of questions. And if you know answers, please tell me, because I would like to know.
I have a question related to this Taub-NUT, because usually Taub-NUT is a fiber bundle of a sphere, of a two-dimensional sphere. Is this scry which you have here is just as free as a fiber bundle over S2, so Hopf bundle, or
yes, yes,
yes,
the scry inherits this bundle structure.
So this is Hopf bundle, yes.
Yes, the scry has the Hopf bundle structure in this.
Hopf bundle.
Actually,
so the fiber is S1, yes.
But actually, if I may, I think that there is at least one parameter for which this metric induced is actually conformally. So you can fine-tune your parameters in such a way that metric induced on this scry is conformally flat. And so then I would guess it's not a Hopf bundle, at least for this very non-generic point in phase space.
The problem of Hopf bundle is that you are in conformal class, so this is conformally related to Hopf bundle, yes. So it's rather one should rather say this way.
Yes,
okay.
I would say it is always a Hopf bundle, maybe endowed with some other structures like metricness, and one may choose conformal factors such that it is not invariant with respect to this U1 group.
Yeah. So I thought about generalized Hopf bundle, nothing with group structure. No.
But there is underlying Hopf bundle structure always inherited from the
Okay. Thanks.
So now questions I'm asking myself and also to you are what are allowed parameters? I'm from physical perspective. So do we have that? Does it make physical sense to consider also all sorts of topological because this Taub-NUT deformation is described by one number. So and it is smooth for all those parameters, but perhaps some are physical and some are not, because usually people think that Taub-NUT solutions are not very physical, for example, because they are not asymptotically flat when you don't have lambda. But when you have lambda, they are actually asymptotically de Sitter. So that's good, at least. Another question connected with this is about global hyperbolicity here, because it seems when you look at those solutions that the usual argument why those Taub-NUT spacetimes are not globally hyperbolic, so again some case against physicality of there, is that they have closed time-lax curves. But you can check that at least for some parameters, those usual suspects are not closed. Or actually they are closed, but they are not time-lax. So you can choose your parameter, your curve, Taub-NUT, mass, and so on, in such a way that you don't have closed time-lax curves. So it would be, I think, it would be nice to understand whether this spacetime is globally hyperbolic, or perhaps there are some other problems. And the third questions.
No. All the spacetime is not globally hyperbolic, but the neighborhood of this conformal infinity seems to be.
Yeah, but I think that for some parameters, actually, perhaps the whole spacetime can be.
Oh yes, I see. You think of parameters when horizons don't emerge. When we don't have horizons or only one horizon, perhaps. I see.
Exactly. Yeah. And another question is, and it will be connected with something we'll see later on, is about...
Sorry, question. Can you have a solution without killing horizons in this class? I thought you always, I mean
Yes, I think that this polynomial which defines, whose roots define horizons, it may have no roots.
No roots whatsoever with the Taub-NUT parameters? Because of course, if you don't have a Taub-NUT parameters, then they always have horizons.
Yeah, but I think that maybe Maciej Kolanowski remembers better, because Panie Maćku, did you check?
I mean, I can say that if you don't have kerr parameter, then if you have pure Taub-NUT de Sitter, then I know that for some Taub-NUT parameters you don't have killing horizon
at all. I see.
Thank you.
At least in those coordinates, in this part of a spacetime which is covered by those standard coordinates of Taub-NUT. But I would like to also know if for kerr de Sitter Taub-NUT solutions, if electric and magnetic part of a Weyl tensor on Scry commutes treated as a 3x3 dimensional matrices or not, commute or not, because it was recently proposed by I think by Alvarez and Sanovia that it is a good test whether there is a radiation in your system or not, that if those two commute, it means that there is no radiation, and if they don't commute, it means that there is a radiation. I didn't actually understand the papers, so I thought that I will try to find some counterexample, and it was my guess. So I wasn't able to calculate it also with kerr parameter, but without kerr parameter, those two actually commute. So it seems that actually this idea is correct, that they commute, and so there is no gravitational radiation. Okay, and the last example comes from Hinz, where he constructed solutions with many, arbitrary many actually, Schwarzschild-like black holes. Introducing different, so basically you get rid of endpoints in of your sky.
Maciej, the question of commuting depends on the point. This is uniform because this is in tangent space. So when I pass from one point to another, then those matrices may change and
yes,
commute in some points and in another not. So
yes, but if you will take Taub-NUT de Sitter with Schwarzschild with mass, but without rotation, then they actually commute everywhere.
So in some sense, this is uniform, yes?
Yes. And the idea is that if you have a region of sky where those two matrices commute, it means that there is no radiation in this region. It's somehow connected with some properties of Bell-Robinson tensor. Okay, so this last example considers, as I said, many black holes. So we can take a lot of points of sky and insert a black holes in those points. They cannot be exactly arbitrary. There is one constraint that must be satisfied. And then Hinz was actually able to prove that there is such a solution that in the neighborhood of those points, when you inserted your black holes, in some small neighborhood, spacetimes are actually isometric to Schwarzschild de Sitter. And then there is a little larger neighborhood in which some very bad things can happen. And then outside of those, you have something which is very, very close to de Sitter. So basically, so that metric induced on sky is actually conformally flat outside of those larger neighborhoods. And in space-time, those corrections to de Sitter are very small and they vanish in the limit. This is some sort of a shielding of, in the case of positive cosmological constant. Okay, so I have also questions about this. So what about scattering? So Hinz proved only that you have some neighborhood of sky, that perhaps there is something wrong with your solution if you evolve it too much into the past. But I would love to see some sort of solutions or even heuristic ideas whether when we prepare some states, some black holes in sky minus, and then there's some very non-trivial evolution, and I have again a picture like this at sky plus. And natural question then would be: does it allow for some sort of topology changes? That I start with 5 points removed, but after this those collisions, after some merging of black holes, I have only 2 points removed. Okay, so those are examples. I hope that now we have this gist of what are asymptotically de Sitter spacetimes. So I will now go to some technical details. In our work, we use Fefferman Graham gauge because it's convenient. I think there is nothing distinguished about this gauge as far as I can tell, where basically we have we have some three-dimensional space-like metric which is expanded in some rho parameter, and rho going to 0, where this metric is singular, is ill-defined, corresponds to sky. Now G1, I think, vanishes. In this expansion, G1 vanishes due to Einstein equations. G2 is determined by Einstein equations, something like a Ricci tensor with some corrections, perhaps. And then G3 is freely prescribed up to constraints. It is supposed to be trace-free and also divergent-free. For convenience, we will write with this G3, which is rescaled by some dimensional parameters, because this is what people in holography do.
Maciej, why not to say that no radiation means that this part vanishes? This is just final initial data of the gravitational field. So no radiation means no field. No?
Which part you want to vanish?
G3.
No, because for example, for Schwarzschild de Sitter, G1, G3 is non-zero, and well, you know that that Schwarzschild de Sitter doesn't have any sort of radiation, right?
I am not sure.
I am.
It contains charge, yes.
Yeah.
So okay, so it's a problem of charge, but if you remove charge, the rest is zero. So up to these charge values, which are special, everything has to vanish. So wave part has to vanish, just this is my intuition about radiation,
Yes, I kind of agree, but I think it's a little bit more complicated because you need to somehow understand what kind of charges you allow in your G3, because you don't only. Oh.
If I may, if you take Schwarzschild de Sitter, GA3 is not zero, so there's no radiation. So just G3 being zero with no radiation.
Is also no radiation, but this is very special field, So I agree that there is charged part, this mass parameter, but the rest is zero.
Yeah, but it's actually not only mass part, because there is, if you take Kerr de Sitter, you also have contribution from...
You have angular momentum.
Yes.
Yeah, I know. As usual, initial data, very special initial data. I agree. Yes.
Yeah, but my point is that, well, since you allow for some sort of G3 without radiation, then you would need to specify what kind of special Coulombic charges you allow without saying that there is radiation.
I agree.
That's the problem.
The main problem is to divide this part into charged part and wave data.
Yes.
So and this is crucial.
Yeah. Yes. And I think it follows from some old work of Penrose that you cannot do this in an ambiguous manner. That only when lambda is equal to 0, you have well-defined division between Coulombic and radiative modes.
Yeah, it depends on G0.
Okay, so now about initial data, those G0 and T are defined up to conformal transformations, and in this Fefferman-Graham gauge, changes of conformal transformations simply are equivalent to the choice of a different slices of rho equals 0, of rho equal constant. Here. So from the pioneering work of Friedrich, it follows that actually this conformal class of G0 and T uniquely defines solution, at least in some neighbor, at least if those G0 and T are close enough to the Sitter solution. And in the case of Fefferman-Graham gauge, it simply means that all those Gn satisfy some recurrence equations, and they're uniquely defined by those recurrence equations. So there are no additional integration constants or whatever. And I think it was also shown by Fefferman and Graham that if this conformal structure on Scry, so this G0 and this T are real analytic, that then this power series is actually real analytic in such a sense that it has a real analytic representative, then this power series is not only formal, but you can actually sum it to something.
Well, this follows from Friedrich already and
Okay.
general results about hyperbolic PDEs. There's a theorem by Alignac and Métivier that guarantees this kind of things.
Okay, that's good to know. Thanks. So that's it.
But perhaps this Graham Friedrich is also valid for negative cosmological constant?
Yes, they are. So that's it about this introduction to asymptotically de Sitter spacetimes. So perhaps do you have questions before we will proceed? Oh, no questions. That's good. Or not, I don't know. Okay, so now we will go to this Wald Zoupas idea of defining conserved charges, which is somehow connected to Hamiltonian charge, symplectic / Hamiltonian definition. So general idea is such that we have some hypersurfaces in our spacetime. Let us imagine for a moment, for simplicity, that we are in asymptotically flat case, and we want to define some charges associated with those hypersurfaces in such a way that the difference between those charges, between charge defined on one hypersurface and another, is a measure of energy or momentum or whatever radiated away by gravitational waves. So basically, that we have some conservation law. This idea is already present in the work of Trautmann, where he considered those asymptotically null hypersurfaces on which you can define charges using asymptotic killing vector fields. Now the difference in our case is that when lambda is positive, scry is space-like, so it looks rather like this, and so it looks rather like this and not like this. But that's the only difference. And now, how do we define charges in some symplectic way of thinking? So we want our Hamiltonian associated to some hypersurface to satisfy the following variational equation, that its variation is supposed to be given by some surface integral with symplectic form. And here I use this crossed out variation because what I mean that in generic case, this doesn't have any solutions. This equation is not integrable, so this expression is not a true variation. So it's not some sort of an operator, but just a suggestion that perhaps this is a fake variation. And I should say that we assume both in asymptotically flat spacetime and in asymptotically de Sitter spacetimes that our hypersurfaces with which we want to associate charges has some sort of boundary, and those boundaries are exactly surfaces where those sigmas intersect scry. So some two-dimensional sections of scry, and using integration by parts, you can change this symplectic current into some variation of a netter charge and some presymplectic and some symplectic or presymplectic potential. And here by psi I mean this vector field for which I want to calculate my charge. And as you can see from this expression, this charge does not depend on the details of this vector field in the bulk. It only depends on its class when we go to this boundary, or at least it should have if it is supposed to make any sense at all. Okay, so we can take the second variation, quote, quote, of this expression, and then we will find our, and then what? Charge, second variation of charge is simply going to be 0, but a variation of this presymplectic potential will generate as presymplectic form. So this second variation is given by presymplectic current, but now calculated at this cross section of scry. And in generic, well, who is to tell that it is 0? Generically, it's not going to be 0. This equation 13 does not define any charge, any functional on a phase space. So the idea is that we should add something in some sensible manner to this to have something which is a true variation, and it's kind of obvious what you should add. Because, well, first of all, this second variation is not given by a true, by the full symplectic form, but only by its pullback, well, first contraction, then pullback to this boundary. So it may happen. Perhaps only some part of a symplectic form contributes. So let us define this pullback to omega with bar, because this is only thing that we care about, and we would like to have some other theta, some other symplectic potential, which variation would give us symplectic form, this or actually pullback of symplectic form. And then we can add it, and obviously when we calculate the variation, it is 0. So perhaps it is a variation of something real. And then you can calculate that in cases that we're interested in, it is so that we can actually integrate this equation, and moreover we can calculate flux of this expression, and it is given simply by this large theta. In general case, it may happen that this small theta is ill-defined on scry. So we need, and only this difference is something that has a correct limit to scry. So the easiest way. Oh, let's just remove this theta part is not always available. And then, of course, we have an ambiguity, because such large theta is not defined uniquely. We can always add to it variation of whatever functional we want. So Wald and Zoupas wanted to have some unique prescription of how to do this. And so the way Wald always does it, he added a long list of assumptions to this, what kind of stuff theta should satisfy, and then he was able to show, they were able to show that actually there is only one such theta. So they wanted it to be built locally out of dynamical fields and universal background structure. So in the case of asymptotically, so you have scry, you have some universal conformal class of metric on scry in asymptotically flat space. This is not something that we have and can use in an asymptotically de Sitter spacetime. Moreover, you want that this that such a term, which is actually a flux, which is roughly speaking a flux of some quantity for scry, is 0 whenever this phi solution is stationary. Because in asymptotic flat spacetime you can talk about stationary stuff because their scry is null. Moreover, it should depend analytically upon those dynamical fields. It doesn't mean that we are in analytic category. So metric, for example, is only smooth, not analytic. But for example, your Lagrangian depends analytically upon this metric. And obviously, it shouldn't depend upon any arbitrary choices, especially a choice of a conformal factor. Okay, so we are now back to the positive cosmological constant case. You can calculate this limit of a symplectic current. It's a little bit non-trivial because it's actually 0, so you need to add some counter terms to your action to have something finite. So it was calculated, for example, by those people, but I think that Professor Jezierski more than 10 years earlier actually calculated it, but in a little bit different form. But as it actually follows from this work of Friedrich, this symplectic, this pullback of a symplectic form is equivalent to the symplectic form from a bulk because we have well-defined Cauchy problem on scry in this case, so we cannot lose any degrees of freedom when going from one to another. And well, it's kind of obvious what kind of theta we can choose. For example, we could choose theta like this, equation 19. So is it unique? It's a natural question. So this is our first guess. You can add to this Hamiltonian, and then you can check that to this variation of Hamiltonian, and you can check that now it truly defines this Hamiltonian, and it is given in such a way. This Ni is a normal vector to this cross section of scry. It was, as you may see, it was actually calculated by those people 10 years ago, but unfortunately they didn't bother with with considering all those ambiguities and uniqueness that Wald and Zoupas did. So we're going to do this right now. So this is again this list of assumptions that Wald and Zoupas made, and we just decided to get rid of this one which we cannot satisfy, because near scry we don't have any notion of what does it mean to be stationary, because it's space like hypersurface. So we just get rid of it, and it's enough actually. So I think it's kind of nice that you need to assume less to get the same result as in asymptotically flat spacetimes, because apparently this is a more rigid structure. The proof is rather straightforward, but I personally don't find it elegant. So if you have some better idea, please tell me. So as we discussed, we can change this theta by an addition of a variation. In this variation, since it should be local, it should be basically integral of some local thing, and this function w, small w here, it can depend on metric, on Ricci tensor. Since we are in since scry is three-dimensional, we only have Ricci tensor, right? It contains all information about curvature. It can also depends upon this T tensor, but also the covariant derivatives up to any order, but let us assume that up to some finite order. Then what we can do is that we can expand it in a power series, because we assume that this expression is supposed to be analytic in our fields. And then we can demand that each term separately has weight -3 under constant rescalings. So we want this 22 to be conformally invariant, but it may be that different terms are not conformally invariant, but their sum is conformally invariant. So it's hard to tell based upon a power series, but what we always need to assume is that each term in this power series has the same scaling upon constant rescalings. Then you can classify all such things. It's not very hard combinatorics, and you can check that the only term which survives is trace of this T tensor. But from Einstein equations, it follows that it is 0. So at least on shell, there is no such term. So for example, in here, you could say, oh, but I could also take theta where this variation acts not on G, but on T. And I would add minus in front, but this is the same theta. Because they differ by variation of a trace of T, and this is 0 on shell at least. So there is truly one such potential. It is actually important that we assume that our expressions are analytic in those in those fields.
Question. So
yeah, sure.
Can you comment again on this issue that each term is conformal invariant as opposed to the sum is? Because of course that's an important
yes, of course. When you expand, it may happen, and that each term is not conformally invariant.
Right. So your argument assumes that everyone is?
What I assume is that everyone is invariant, I mean, actually covariant or invariant after this multiplication by this measure, that it is invariant under constant rescalings.
This is not obvious, right? I mean, you could imagine that there are things which, or it is obvious, then this must be.
I mean, well, first of all, okay, so you can see just looking at all those terms that they must, that each term must, that when you rescale, each term must simply be rescaled by some power of this rescaling. That you cannot have anything different. And then you could, you know, take derivative with respect to this rescaling, go to 0, and something like this.
Okay, thank you.
Thank you. Yeah, so back to the topic, it is important to assume that this expression is supposed to be analytic so that we have this power series expansion. Otherwise, we could take something like this square root of cotton squared, because cotton is conformally invariant in 3 dimensions, but here we have also cotton with raised indices. So you can check that actually such W would be conformally invariant, but its variation would behave catastrophically at conformally flat data. Like the sitter, for example. So we need to get rid of it, and the easiest way is to assume this analyticity. Okay. Now the problem here is that it follows, since we have such since the only structure that we have available is this smooth structure. We don't have any conformal class distinguished or something. It follows that all diffeomorphisms of this scry are asymptotic symmetries. And this is large group. It's much larger than the sitter group, and even it's much larger than BMS group. Right, so in a sense, our prescription can be applied to any asymptotic symmetry. So any vector field on scry, so it generates way too many charges. So even if we would take something like de Sitter, which is as close to stationary solution that you can imagine, and I'm sure that everyone agrees that there is no gravitational radiation in de Sitter, you could calculate just by choosing some very stupid vector field, you could generate non-zero flux. So those are obviously non-physical fluxes. However, if you look at this constraint, which follows from Einstein equations, it actually implies that at least some of those vector fields are actually generated gauge transformations. So despite the fact that we are at infinity and they act on a boundary, they are actually gauge transformations. It can be shown that if you take the quotient, so you take all diffeomorphisms and then you take a quotient by those which are actually gauge transformations, you get the sitter group, which is quite nice. This is true at least assuming that we are topologically in the cylinder case, as I will now assume. And we also need to assume some decay conditions at the cylinder when we go along this real line. But the problem is, can we actually distinguish the sitter algebra within all vector fields? because you know, quotient is not a subgroup or a subalgebra, whatever you like. So it doesn't follow that we know how to define physical charges, and there is some idea. This idea is rather, for now, it's rather geometrical. I'm not sure what is physical content behind it. So hopefully it will become clear at some point. This idea is to introduce frame in which the symmetric is of such form. So this is kind of like a radial gauge, and we assume that determinant of this metric QAB is some fixed function, for example, determinant of a standard sphere. Okay, I see that someone wrote something on chat. Okay, never mind. In fact, also let me just comment that a few days ago there was some other proposal by Fernandez, Alvarez, and Sonovia, also how to define something as connected in the same context of asymptotically spacetimes, and they had some other foliation of Scry, and I think those two are very similar. I would need to check it, but I think that it may be that those are the same. Those are actually the same foliations, but expressed in different language. This condition 25 is actually nothing new. In asymptotically flat spacetimes, it was proposed, or rather, its conformal equivalent version. It was proposed already by Kijowski in 80s. And moreover, I think it was shown in 85 that under appropriate appropriate boundary conditions, that there is unique structure like this. So if we assume that we can propagate this de Sitter, we can first of all introduce such a distinguished section, but as I said, it's rather distinguished by geometry, not physics, and then we can use it to propagate the Sitter algebra from -infinity to the whole Scry using this d upon du. But not everything about it is obvious. So as I said, I don't understand physical meaning of this construction. And second of all, what kind of initial and final conditions are allowed? So from this work of Professor Hrušťál, I think we have something, not such strong boundary conditions or initial conditions as we would like to have, but it seems that because there are some differences between asymptotically de Sitter and asymptotically flat spacetimes, but it seems that they could be strengthened a little bit, but I'm not sure if enough for our purposes. So this is something that we still need to understand better. Okay, before I will continue, two questions. First of all, how much time do I have?
You have enough time, I would say. 15 minutes.
Okay. And the second question is, so I'm going to finish this section. So do you have any questions to what I was, what I told you up to this point? Again, no questions. Okay. So perhaps I will just comment quite briefly on this. This is actually some earlier work. That some other thing we could do is consider perturbative theory. So, for example, linearized theory on the background of the sitter, and then you can calculate energy flux in boundary coordinates. It was calculated. Oh, actually, oh no, I even have it here. Okay, so it was calculated by Professor Huschel, Hocke, and Tomek Smoke, and also by Professor Lewandowski and myself. And those expressions have correct limit as lambda goes to 0, and they correspond. They agree with our. They agree with our notion of those Wald Zoupas charges. So basically, this is just quadratic Taylor expansion up to quadratic terms of those Wald Zoupas fluxes. We can similarly treat perturbations around the Schwarzschild de Sitter, because we have some distinguished rotation generators and time translations. This was done before this idea of using minimal surfaces, so perhaps it can be enhanced a little bit now. And this is, I don't know if Professor Jezierski is still with us.
No, he's not.
Oh, this is quite unfortunate, because actually you can check that there are some solutions to those linear equations which has only magnetic part of the Weyl tensor. So electric part is 0, and I mean it's not 0. It's given by, it's the same as of Schwarzschild, and you have no zero energy density in this flux. The whole energy, when you integrate it for the whole scry, is actually 0, but you have some non-zero flux in some regions. So it kind of, I think it may be in conflict with Professor Jezierski's idea that you can simply say that, oh, if this this electric part of a Weyl tensor, which is basically this T tensor, is of this Coulomb type, then you don't have radiation, because at least in linear theory you have such solutions. They are not probably very physical, for example, because as I said, the total flux of energy is 0, so you have some negative energy, some positive energy in different regions, but nevertheless density is non-zero. We can do something analogous for Kerr de Sitter, and this is actually nice, because here you could ask what kind, because angular momentum generator for Kerr is kind of uniquely defined, because you have this d upon d phi, and you say that this is good because it has closed curves. So this is how you can distinguish it. But d upon dt is not so much distinguished, because you can add to this something proportional to d upon d phi. And actually there is such a choice which makes this scry non-rotating. So this T is hypersurface orthogonal, and this is exactly this. Then this energy time translation generator is exactly this d upon du from here up to constant term, I think. This is some other road that leads to this idea of minimal surfaces. And we have checked that you can do this on Kerr de Sitter, but there is then this idea how we can extend it far from Kerr de Sitter, perhaps using this minimal surfaces scheme. Okay, so to conclude, we derived charges and fluxes in asymptotically de Sitter spacetimes. Their uniqueness follows from some set of quite natural assumptions. They seem to give physical results on the background of Schwarzschild de Sitter and Kerr de Sitter, and they recover classical results in the limit of lambda goes to 0. But how to define energy in the full theory is still open. We have some ideas, but we still need to understand them better. And I have a few open questions to finish. First of all, what is physical meaning of this foliation by minimal surfaces, as I was saying over and over? Second of all, how to define Mu's tensor, and do we actually need it? And there is a way how to define it, recently proposed by Fernandez, Alvarez, and Sonovia. But again, this is rather geometrical and not physical prospect as far as I understand it. Then there is a question of positivity. Is this flux of energy positive for Scry? And obviously the answer is no, because Scry is time-like surface, so there is no reason for flux for it to be positive, definite. There are some ideas that if we could implement no incoming radiation condition, that this gravitational radiation is only produced by some masses within our universe, and we don't have any gravitational radiations coming from infinity through cosmological horizon, then we should have positive definite energy flux. It was checked in linearized regime that it is actually so, but I think it is an open question how to define no incoming radiation condition from the point of view of a Scry, to distinguish whether we have radiation which was generated by some say merger of some black holes and not something that was put by hand at the cosmological horizon. There are some issues with lambda going to equal 0. So in those work I mentioned earlier in linearized or actually quadratic theory, we get proper lambda going to 0 limit, but in this work by Compare, Fiorucci, and Ruzzuccioni, they get some singularities which they needed to cure by adding yet another counter terms. They use different gauge because in both those papers in linearized theory we used some sort of anti-radial gauge. So basically, and they use this radial gauge that I discussed before. So perhaps this is because it seems that to go from one gauge to another, you perhaps need to do something at infinity. Then, well, it would follow that it's not actually a gauge, but symmetry transformation, and this is the reason. But we are not sure of it. I think it needs some discussion to check it. There is also a question of observational perspectives, which I promised you in the very beginning. So you can calculate a lot of stuff, for example, in linearized theory around de Sitter, and you can get some. You can get, for example, modified quadruple formula, which depends somehow on lambda. But the point is that we don't actually live in the Sitter universe. We live in some expanding universe, which is filled with a lot of things. It had very disturbed history. So it's not obvious how to go from this result to the full cosmological picture. The easiest thing would be, okay, so we have lambda, which is very small, by the way, but we can change it to Hubble constant, which is but then the question is, should it be cosmological constant at the moment of emission, at the moment of observation, something in between? And basically two scenarios, there are two phenomena which can affect our answer, which we cannot distinguish at the level of de Sitter. So first of all, this event which generated black gravitational radiation, for example, merger of two black holes, could happen in highly dynamical space-time, which was expanding, for example, at a very high rate. So this is the first change from your usual assumptions about linearized theory in Minkowski. And the second thing is that then this gravitational radiation needs to propagate it in expanding universe. So, for example, Huygens principle is not satisfied, and so on and so forth. And unfortunately, in those linearized models, we have those two phenomena at the same time with the same parameters, so we cannot distinguish between them. And from some phenomenological reasoning of Beatrice-Bonga, it follows that if the main aspect here is that event happened in quickly, for example, just after inflation or something, then we can measure differences in the next generation of gravitational waves. But if the main change is not due to this, but due to the fact that actually those gravitational waves are propagating in some non-trivial background and they are changed slowly and slowly, then actually, unfortunately, even after a very long time, this effect is very small and we cannot check it. But to distinguish between those two properties, we need to do some really complicated numerical analysis, and we are not yet ready for this yet. And another thing that one could do would be to try quantize this system, because those constraint equations at Scry are very simple. So they're much simpler than in ADM formulation, although those are basically ADM constraints. So one could hope that perhaps they could be quantized, and in this way we would have some Hilbert space, at least associated to infinity. But if we were able to quantize both I minus and I plus, one could consider some analog of S matrix from one to another. And perhaps it would be perhaps also interesting to see this expressed in loop variables and how what those components, like for example this energy electric part of the Weyl tensor, looks in this either Palatini or Ashtekar language. Okay, that's really the end for today. So thank you very much.
Thank you very much for this interesting talk and questions, comments.
So can you say something more about this idea of taking this global conformal, conformally minimal foliation? I mean, why should this be the right thing to do? Why should this be physically the right thing? I mean,
unfortunately, I have no idea. So basically,
many other possibilities. Right?
Yeah. Basically, this was proposed by Compare, Fiorucci, and Truziccioni 2 years ago, and but what they actually assumed is that they have such a God-given structure on Scry. What was recently done by Senovilla was again the same, that they assume that they have some distinguished foliation of Scry, and for some reason they know that this is distinguished foliation. So I don't really know. The point is that as follows actually from your work, it follows from your work that you can say that there is, in this class of foliation, there is distinguished foliation given by what happens at minus and plus infinity.
Right, but I mean, of course, but I mean, one can write.
I cannot say if there is any good reason. Okay, perhaps some reason was, and this was motivation behind this, is that if you then calculate algebra preserving this foliation, it is somehow lambda deformed BMS algebroid.
Of course, the reason why Kijowski introduced this, that he had when you have this representation of the metric, then he could give a very simple proof of the positive energy theorem. But there was no physical meaning associated to it, right? But while these people are trying to make some kind of physics out of it.
Yeah, I cannot comment. I think that if you want to have this this sort of foliation, then there is this good foliation which comes from your work, but I cannot. It's hard for me to comment on the larger picture.
Okay, thanks a lot.
Thank you.
This condition is also in asymptotically flat spacetime is a luminosity condition too, yeah?
No. I mean, it's much stronger than luminosity condition. So luminosity condition is indeed that this metric is fixed, but you can have some mixed terms in 1/r expansion. But here we have stronger conditions, but only on a metric induced on scry.
Okay. I have to look into this paper because
so this is it happens on the scry. The luminosity condition is in bulk, right?
Yeah, but this is in fact I have to look into these papers by Synovia. I did something similar in the sense that on the scry, from my point of view, the best condition is that this determinant of this matrix QAB is determinant of the spherical metric. So it looks like luminosity. Okay, some other questions or comments?
Hi, can you hear me?
Yeah.
This is Jahan. Yeah. So actually, I have two questions. So at some point of your talk, you mentioned that Wald and Zoupas also give a flux formula for asymptotically flat spacetime, right? And at some point, you mentioned that so they choose the answers for fall-off in terms of unphysical metric. So at some point, you mentioned that their answers doesn't work for lambda equals to 0 case, which I also believe their answers actually should not work for lambda greater than 0 case. And do you have any comment on that? You can go near I think equation 14.
Oh, 14. Okay.
Yeah. Equation 14 near.
Equation 14. Okay.
Yeah. So I believe this 0 condition will hold depending on if there is no flux on scry, and that actually depends on if your symplectic structure omega is 0 on scry or not, right?
Yeah. Okay. So
I think for non-radiating case, Wald and Zoupas assume that omega should be 0 on scry. For that, you have different fall-off condition. But if there is radiation, they choose some different fall-off for unphysical field, right? And they derive a flux law for asymptotically flat case. And the comment is that their answers cannot be promoted for lambda greater than 0 case. And what I'm trying to say that, do you have any comment on that? So Wald and Zoupas also derived a flux formula for unphysical space-time. So they converted all these things in terms of unphysical space-time, and they have a flux formula in terms of, I think, linearized perturbation, but in unphysical space-time.
Yeah, but I think that this result is conformally invariant, so it doesn't depend on whether it is in unphysical space-time or not.
Okay, and their answers, so they have a specific answers, And do you have any comment that their answers will work for lambda greater than 0 or not? Because their foliation is completely different from the Bondi foliation. That is completely different. They ad hoc, they choose the ad hoc answer. I think they choose some fall off, and they show that for asymptotically flat case there is a flux law.
Yeah,
in terms
I'm
of
afraid I
perturbation,
cannot
actually.
comment on it right
Okay,
now.
okay. And my second question is that can you just go to your equation 26?
Equation or page?
Equation 26.
Okay.
Yeah, so maybe
Oh,
I
actually,
am,
it's the same, yeah.
yeah. So maybe I am understanding something wrong. So this flux formula is a three-dimensional integral.
Yes,
So
it's
it is not a flux across S2, right? So it is a
yeah,
total
so
energy.
this is a flux across scry. So I
You
mean,
mean
this
that
is to get flux, you would need to integrate it along.
integrate over the three surface,
Yes,
not
three surface.
two-dimensional surface.
Yeah.
Okay, and what kind of space-time you are choosing working on here?
Here it is on the background of the sitter. So,
So it
this
is
sky, but we are working
linearized
in
case.
Bondi coordinates, so it's a cylinder.
Okay, and it is also linearized case, right?
Yes, yes.
I see. And okay. Okay, thanks.
Some other questions? If not, thank you very much again. So we finished our official part. If you want to stay online, you can do, and you can discuss more.